Okay, so we are going to wait for a couple of minutes because the access to the room is not so easy, so I prefer to wait for a couple of minutes for the latecomers. Ok, je vais démarrer. Okay, so I propose that we start. So welcome to this session, this morning session of the Battery Innovation Days that will be addressing how the digital twins can really bring to the production of the battery industry. So if we can move to the, oh yes, sorry, I always forget that I can move the slide myself. So digital twins for manufacturing, we will be having a very interesting panel discussion in the second part of the session, but before we go to this one, we will have some overview of what digital twins mean for battery manufacturing, with first a presentation from, let's say, the eyes of the research people that will be provided by Dr. Elisabeth Ayerbe, which is a team leader in CDTech RTO in Spain. And then we will have also the presentation coming from providing the view of the industry that will be provided by Niccolò Manfra from Mans, Italy. So I forgot to introduce myself for those who do not know me. So my name is Philippe Jacques. I'm the Managing Director of EMIRI and acting also as Secretary General of BEPA, the Battery European Partnership Association, which is partnering with the European Commission in the BAT4EU partnership. So without further delay, I propose to give you the floor to you, Elisabeth, for your presentation about what really research is doing on this very interesting topic of digitalization and more specifically digital twins for manufacturing. The floor is yours.
Thank you, Philippe, for the introduction. Thank you, the organizing team, for giving me the opportunity to be here to give you an overall picture of what digital twins can provide to the manufacturing of battery cells. So I'm Elisabeth Ayerbe, as Philippe said. I'm working at CDTech Energy Storage. In particular, we are working at cell level, and our core activity is in the pilot line, and in which we manufacture prototype cells up to 50 ampere-hours pouch cells. So the idea of developing these digital twins is somehow to improve the manufacturing of our pilot line, but be capable to scale up to other further scales like gigafactories. So let us start with the challenges in the manufacturing. We heard this morning that there were main challenges, and we can divide it like in three main pillars. The first one can be the sustainability. We have this morning a lot of as well in the sustainability, also on cost efficiency and high quality. But these are the general aspects. And then if we return to the specific manufacturing pilot lines in which we enter material, we need to jump from one step to the other up to the cell level, and then we need to carry out the formation step, and then we need to also address at certain point how the cells are aging. We need to understand properly all the parameters that are affecting in each of the steps and intermediate products. So basically, sustainability is critical because obviously we need to ensure that what we are manufacturing is eco-friendly or environmentally friendly. And one of the steps in the manufacturing that it's very much linked to this eco or CO2 footprint is the drying step, because we have a solvent evaporation, NMP. This is the typical processing method, or at least what we are using at our pilot line, roll-to-roll pilot line. So we have an NMP evaporation, and we have to deal with this. And even also this drying step, it's very energy resource, or it's very consumes a lot of energy. So you need to find a threshold in which you trying to minimize the energy consumption. This obviously optimize even the solvent evaporation, and then you can need to fix the outcome, which is basically the microstructure, and in there you have many mechanisms you have to deal with this. So this is particularly important to have tools that can enable this kind of correlation between parameters that are from the machines, processes, the outcome, which is the product, and the cost and energy consumption. So sustainability is crucial, and obviously in the drying, we can think on recovery, the NMP, and going back to the line, but there are also ways to optimize this specific step. Then another crucial step is the high quality, and what we want to have is high quality cells, means that we need to minimize the rejection rate. So as we all know, manufacturing is a very complex system, which we have many steps. They are very much correlated, and all of them might impact on the intermediate, but also in the final and the degradation steps. So optimizing, trying to get maximum high quality means minimizing rejection, but not only that, is that we want to maximize performance. So it's not only putting it in a camera to ensure that in the coating machine you are minimizing the rejection, but it's also correlating how the calendering parameters might impact on the mechanical properties, and then these mechanical properties of the electrodes might impact on the cell performance, cell aging, and so on. So it's again another example of how important is and becomes the correlation of different parameters with the outcomes, processing, and machine. And lastly, cost saving. Obviously, we need to carry out and we need to manufacture even prototype cells at very lower, or trying to minimize the cost. And one option is to push for high productivity, I would say. So high productivity can be, for instance, running a very high-speed coating machine or drying step. But this can ensure that you will have a good performance of the cell. So again, it's a matter of a trial. So speed will have very much impact on the microstructure in the drying step, and later in the calendering, and for sure will have again impact on the performance. So what the message here is how important can be the understanding and the knowledge of the interaction of particular parameters onto the outcome, and the outcome is performance. And cell aging. So, and this knowledge can be gained through models, and basically digitalization here is crucial. Digitalization is very broad, but the thing is that it's a coupling between models, data, communication, IT platform, and all together so that the user or the worker or the researcher can make decision over something that is really understood previously. So, yeah, and the current trend is that in general, the manufacturing is moving from the intelligent manufacturing, where obviously you need to know something and where you decide, you make decision over something, to a smart manufacturing. And this is particularly important where and data comes into play. So data acquisition, data creation, and data usage and treatment is crucial together with the models, because the way you obtain the understanding is by a combination between having the real data with the knowledge that physics-based models can give you, and then you make over the decision. Obviously, for having this smart manufacturing, and this is the way we visualize these digital twins, is that you need to have technology enables, and obviously this is a combination of many technologies, like as I was saying, physics-based models, data-driven models, communication platforms, IoT, virtual reality, augmented reality, many aspects that bring together to something that is called smart manufacturing, but gives a huge amount of information, huge amount of knowledge in order to make a proper decision over the manufacturing plant, not only at the pilot line, but also at the further scales, like gigafactories. So, and what is a digital twin? I already said that what is the process of digitalization, that it has different processes, and in reality what we want to have is something that mimics the reality. This mimics the reality means that it's exactly the same but in the virtual mode, and this virtual platform has the capabilities to give information so that you can control the real plant. So we need sensors, we need to acquire data that can be done manually or automatically, but we need to have this data in place so that then we can make over decision. And this fits into something that is called digital twin or platform, in which we have like different aspects. And one aspect is that you have to take this data and you can store this data, and obviously you can manage the data and treat the data, and then make a decision over this data. Another aspect in which it's very important in the digitalization is the modeling and simulation, where you can gain more understanding on the physics behind, because coming to the drying, we have many parameters there, and you have a sedimentation of the material, you have a solvent evaporation, but you have also binder migration and additive migration, and you have to properly analyze and understand what is going on in between the machine parameters, because it's what we are talking about is I can control the machine, but then I need to figure out what is going to be on the microstructure, because I know that if there is certain heterogeneities on the microstructure, we might impact on the performance. So modeling is crucial, and these physics-based models, together with maybe enhanced data-driven or surrogate models, it's really a powerful tool in which you can then make over the decisions. Then we have a digital twin that is somehow that connects these models into the real platform, and through gaining the data, and then you can make decisions over comparing the data to the models, then you can control the reality of the tool. This is the digital twin, and then I will just show some examples. So, and then we have obviously the civil physical space, in which basically as the digital tool Digital twin is more focused on the models and data that is coming from the real plant. The civil physical system is basically more on the field of data and treated data, and obviously you can make decisions over this data. So this is the difference between the digital twin and civil physical space. Then I will show some examples, as I said. So, and lastly, the visualization platform, because in the end, what we want to have is something that is visually attractive, and so that or even the worker or researcher or whoever can make decision and can even control if the calendaring machine is somehow not pressing at the pressure you would expect, so that you can stop in the right moment, and you don't need to wait until all the rolls are manufactured, and then you discover that the machine was not working. So this is particularly important in this. It's very much important in this digitalization as well. So the idea now is to show some examples and to show how important can be on the understanding, on the scope of understanding the digital or the manufacturing part, and then how we can use this tool to different purposes. So there's a work by Snell in which they are implementing data mining over the data that they have acquired automatically or even manually, and they have performed data mining so that they can establish certain patterns. And what they are claiming here is that they have identified the critical process parameters, machine parameters, so that they can later know exactly which can be monitored. And this can be really interesting if you want to scale up certain process, because from pilot line to the lab to the upper scale. So in this scheme or in this work, you can identify these parameters, and then you know exactly that these are the ones you need to monitor, and this will be in the Gigafactory as well. So this is one of the potential uses of data mining. There is work by Professor Tiede here. So I just wanted to show this paper because it summarized perfectly the work of the civil physical system production, in which you can communicate with the civil world and the real world through the data. That again, it's obviously that certain data mining has been performed previously, and then through this communication you can control directly the real plant, because again, you know exactly which are the parameters that might impact mostly on performance. Another example, or what I was saying, is that modeling is crucial, and modeling in the manufacturing needs to be seen as a multi-step, multi-dimensional, multi-scale platform in which we have products, we have processes, we have machines, but we have also environment. So what I'm saying is that obviously processing models are crucially important, because we know exactly how the microstructure will behave at a certain point, but then we need to correlate this to the machine, in which I will stop, I will start, there will be energy consumption, and then there was, so everything needs to be somehow correlated, and because otherwise you lose certain information. And obviously, environmental parameters are very much impacting on the dry, for instance, in the drying step, because at least in our facility, everything is open, and depending if it's winter or summer, the drying steps will behave completely different. So it's really important to have a coupling models in which you can gain much more understanding at different scales. But in that way, and having this information can then make decisions. So there are certain examples. The work led by Professor Alejandro Franco in the artistic project. They are currently developing advanced physics-based models in the processing and manufacturing of the cell. They are enhancing models with artificial intelligence, and then the idea obviously is to optimize certain performance of the cell knowing, correlating all this together in a specific platform. Then later, I guess, Alejandro will extend a little bit more on this aspect. There is a European project, de facto as well, in which we are working on developing processing models in which we are correlating these specific influences on the processes parameters into the performance. And in particular, in de facto, we are very much focusing on the mechanical degradation because we know, obviously, it's, everybody knows that in the calendering step, you fix the final porosity, but it also depends on the drying step that depends on the homogeneous or the heterogeneous of the binder, might impact very much on the mechanical properties like adhesion and the cohesion, but also then will have very much impact on the degradation aspect. Then there are the different works, and from TU Braunschweig, they are working on the process modeling and correlating these process modelings together with performance. I know they are also working on the process models, cell model, and also production models. And then this is an example of the real digital twins and how this correlates the real scenario with the tool, digital twin, in which in this case they are coupling the three aspects, the environmental aspects, the machine, product, and obviously the process. So this is very much important if we want to correlate and somehow improve the battery manufacturing scales. Lastly, I was showing a visualization platform because what we want in the end is to have something that is fancy or based on a web page or whatever, in which the user or the worker or the researcher can control through this web page platform. So this can be done by building 3D models, but then there are also certain works, like the one presented by Alejandro, in which they are working on the virtual reality and augmented reality. And it's true that it's being meant to, or one of the applications of these tools is for education purposes, and it's really important, and we heard yesterday about the needs of the education and can become crucial having these kind of tools, but also these tools can give much more information because you can see inside the machine if certain parameter is not the right one, and then you can somehow improve it. So, yeah, and finally, I wanted to point it out, the work we have done in the Battery 2030 Plus is on the developing on the roadmap, and manufacturing is also covered in the roadmap, and it's it's intended to visualize through the digitalization as well. So we have summarized the closed loop in the digitalization in the roadmap in a way that obviously digital manufacturing and digital cells need to be coupled, and somehow performance aging needs to be correlated to these parameters in the manufacturing I was talking. But it's not only that, it's that we need to build in a flexible way, because maybe we are now talking about to roll in the lithium-ion manufacturing in pilot line scale, but who knows that maybe we can jump at different manufacturing routes. They were talking about extrusion, 3D printing, recovery of the NMP. So there are many, many option adaptability capabilities. So it's true that when we are talking about the digital twins, we need to think in the flexible way to accomplish also that. I don't want to forget about the standardization. Standardization refers here not only to the models calibration, models validation, but also to the data acquisition. Which are the data we need to monitor? Which is the technique we use to measure that? Because depending on the technique, we can see different values and maybe that are not comparable. And like a closed loop, and finally, what is Battery 2030 Plus is about big map, self-healing and sensing, but we don't forget about the manufacturability, because in the end, we need to be ready for what is going on in the next years in these aspects. We need to know exactly how to insert sensors into the manufacturing chain, and also in which is the right position to put these sensors so that it cannot modify the cell performance, for instance. So this is very much interested, and we need to think in a very open, holistic way so that everything come to the base. And don't forget about the recyclability, because although we are very much focusing on the cell performance, cell aging, we need to also have it in mind. So yeah, maybe I guess I don't have much time, but anyway. So just to summarize is that we are on the way to, we should continue on the way to build this smart manufacturing, and I don't forget about data acquisition combined with physics-based models and data-driven models in which with this knowledge and this understanding we are able to make decisions. Something on the data acquisition is that they can be automatically, manually, but it's true that we need to standardize the way we obtain this data, and we need to establish protocols, and maybe Simon Clark will extend a little bit more on that field, but ontology is crucial in this aspect as well, not only on the map, but also on the manufacturing as well. So, yeah, and finally, obviously, we need to also consider the flexibility, adaptability to the new technologies, but also new manufacturing factors, new manufacturing routes. So, and finally, how about including human into the digitalized work? So thank you very much. With this, I would like to end.
Thank you very much, Elizabeth. I let you breathe now. I think it was very intense and very rich. I'm afraid we don't have time for questions, but I'm sure that the clarifications will come also during the panel. Thanks again. And now I invite on stage Niccolò Minafra from Mans. So Niccolò grew actually with batteries because he has a PhD working. He made his PhD working on solid-state electrolytes for lithium-ion battery application, and then he moved to MIT in Boston, where he was focusing on lithium metal anode batteries. And since 2021, he joined Mans, now working on process development for the future battery technologies. Please, Niccolò.
Thanks so much, Philip. And obviously, before I start, I would like to thank you, thank all the people that made this event possible. This has been an amazing 2 days, and we're glad to be part of it. And I would also like to thank the organizational committee to have invited Mans to speak on such an exciting topic, such as digitalization and digital twins in battery manufacturing. Before we start, my name is Niccolò Minafra, and Philip did a great job at describing myself already. But I work in the field of process development of future battery technologies in Mans. Today, we'll be focusing on how modeling and simulation can really advance battery industry, and I will provide a brief, sort of a general overview of how different digitalization can really impact the whole battery value chain in Europe. And we'll touch upon the digitalization onto the manufacturing field. And in particular, I'll provide 2 examples that we involved as Mans. And in the end, we'll just draw some conclusion. We'll go over some perspective, challenges, and so on. Okay, so now that we start, we should ask ourselves, what's needed to improve the ecosystem, the battery value chain in Europe? So in Europe, there is this landscape. It's even ever growing with new gigafactory, but how can we support these realities? And how can we really, once again, improve the battery value chain across Europe? This effort is taken upon the main European associations that we saw today. They actually made also this event possible. And we also like to think that Mans is somehow contributing to develop and help the development of the battery value chain in Europe. The innovation, especially the collaboration, is at the center of Mans' philosophy, and we are involved in many associations, as you can see on the screen here, and also many Horizon projects. I'll show an example later on. And of course, the latest IPCI project, where in this project, we try to develop the future battery technology starting from the 2020 to 2027 with a clear roadmap in mind, while we go from R&D to optimization of pilot lines and then to final mass production. Now we'll get to the point, right? So we'll discuss about digitalization, right? So how can digitalization really improve the battery value chain, and how somehow digitalization is involved in the different steps, or allow me the word layers, within the battery value chain. This is a quite general slide. I'll try to go very quickly, but in the battery value chain and in the European ecosystem, or in general, we have many layers and different stakeholders that really are part of these layers. Well, the first layer will be the R&D, prototyping, and digitalization. Here, with new machine learning methods and algorithm can really help speed up the material discovery, can really help prototyping new cells, new designs. But also in the middle layer, where we actually involved in terms of manufacturing or producing the equipment that'll make the cells, new digital twin concepts will help and will speed up how batteries are produced, producing more efficient technologies, producing more sustainable technologies and devices. Last but not least, digitalization, data sharing, and a clear story and cycle life assessment of the product can really help also the end of life cycle or layer of the battery ecosystem. So digitalization is really all over the slides, but the way I depicted this as isolated square, it doesn't really make justice to the actual ecosystem, because these different layers or cycles are correlated to each other. And if we think about having a whole platform or data sharing between the different stakeholders within the different cycles, this will really help improve the battery ecosystem in Europe. Okay, so now we'll be focusing onto the middle layer, especially the manufacturing, the equipment manufacturing. And I mentioned a lot digital twin. We've heard about this word a lot. And Elisabetta did a great work in explaining what a digital twin is in the previous speech. I'll try to give my take very quickly and very schematically. A digital twin is nothing else than a virtual replica of an actual physical and complex system. And the way we think about a digital twin is by following, we may think about digital twin following this block diagram. So we'll start from a physical-based simulation. Then we have then a representation, a 3D representation of a system, a process, a device, anything really. This representation in this physical-based system can then inspire engineering of an actual system, process, or device, once again. And once we make the engineering of that system, we actually start working with it, producing data, we'll have the feedback. So we'll feed back the data from the real device into the algorithm, and then we'll have a continuous improvement of our model, because it's not only based on physical data, it's also based on physical laws, but also data that are produced in the real device. So this will make an even better continuous improvement of the cycle. But how can this be applied to the battery manufacturing or to the automation of the batteries? This, once again, applies in different cycles or layers. When we talk about battery manufacturing, we think about a machine, right, that makes certain type of batteries. But of course, during the production line, there are many machines that make different processes. So we can expand this concept for each of these processes of the machines. And so the process is the inner shell of any automation, of any producing of the procurement of any device. And so with digital twin of processes, we can really better understand the physical parameters that regulate the actual process. And then building upon this, we have many processes actually characterize an actual automation machine. And we can make digital twin of machines to really understand and improve the engineering of the system. And when we talk about different machines being part of a line, we can use digital twin modeling and simulation to really improve the efficiency of the line. So now I will provide two examples of how modeling simulations and digital twin can be applied onto the manufacturing field. Here, it's actually a real case that we're actually employing right now. So here we're talking about digital twin of a winder. A winder is an automatic machine that makes cylindrical cells. So in this case, what we did was building a virtual replica of the actual machine. So a virtual replica that behaves like a proper machine or as a close approximation of a proper machine. And then what we do is that we let the machine run. And so in this way, we can actually test the machine before the machine is even built. So you can imagine the impact that this has on the commissioning time of the machine itself. And this does not stop only at the mechanical level, but also at the software. So in this virtual replica, we can implement new softwares, test the softwares for bugs, test the engineering for bugs, and really understand better the machine itself and reduce and shorten the time to market of our products. Another example, this is not a real digital twin, but it's a way to show you how models and simulations can really help battery manufacturing. And here we're talking about the production in a gigafactory. So how can be this optimized? There are programs that can actually simulate a gigafactory where we have different input data, such as machine footprint, energy, throughput of the machine itself. And then by simulating these machines into the program, where the program itself will help us understand and optimize the efficiency of the line. So as you can see in the representative plots on the right side, from an unoptimized line where the yellow blocks represent the machine that's been blocked by the previous one. And this is obviously a scenario that we don't want to be at, because we have the machine that can actually produce fast, but it's blocked by the previous one. We definitely want to avoid this. And by using these programs and simulating years, months of production in a few minutes, in a few days, they can really speed up and help develop the efficiency and develop the actual production line. So now getting to an end, right? Let's try to draw some conclusions out of this and give us our perspective on what's needed, and I'd like to discuss more into the panel later on. Benefit of digitalization, really trying to answer how modeling simulations can help battery manufacturing. Well, this is really clear. We'll make faster batteries, we'll produce machines shorter times via virtual commissioning. We can, of course, increase the reliability of our products because we've tested them many times on the computer before to actually build them. And there are two spillover effects that digitalization can really bring upon the European community, and this is improved collaboration between different stakeholders into the value chain, and of course provide a transparent cycle life assessment by sharing data, by having different stakeholders that will share data within a network, within an infrastructure, will help us assess the whole cycle life of different batteries. Challenges, there are many technical challenges, and I'm sure the guests of the panel later on can really dive into details of this, but we need, from our perspective, we need faster modeling and more accurate modeling that can keep up with the production rhythm of the different machines, and more and more and more accurate. At the end, there are two perspectives here that I'd like to offer that applying different methods such as machine learning, such as digital twin, we can maybe create plugins into our machines that will self-optimize themselves. Via process it's running, then the machine will understand better the power of the process and will, in the end, understand even how to improve it. And also provide an holistic approach of how different machines can really be interconnected to each other to then produce a very efficient production line of battery equipment. And with that, I'd like to thank you all for the kind attention, and of course, the organizational committee again for inviting us, and look forward to discussing with you.
Thank you. Thanks a lot. Thanks a lot, Niccolo. Thanks also for being able to keep your timing slot, so that's great. I invite you to take one of the seats because you will be our industry voice in the panel discussion, and I also invite now the other panelists to come on stage and to take a seat, and I will introduce you when you will be in salle there. Okay, so if I move from left to right, so I'm not going to reintroduce you, Nicolo. So close to Nicolo, we have Professor Maitan Berisibar, who is the head of the Battery Innovation Center in the MOBI unit in VUB here in Brussels, and professor also at the VUB Brussels. We have Professor Alessandro Franco, who is a professor in the Université Picardie Jules Verne in Amiens. We have also with us Dr. Simon Clark, who is a research scientist in SINTEF in Norway. And last but not least, we have also Professor Sebastian Tieder, who is a professor of manufacturing system in at the University of Twente in the Netherlands. So welcome all of you, and thanks a lot for joining us today. I think we have a very great panel with a very variety of knowledge and expertise. So really the first, I would like to come back really to some aspects that were already touched in the presentation, but I really would like to start first by asking you, what are really for each of you, what would be the 2 or 3 key challenges that need to be addressed really to benefit in the best way of this digital approach for battery manufacturing? I don't know who wants to start. Please. Sebastian?
Okay, so I start. Hello from my side. Thanks for having me here in that nice panel. Yeah, the challenges, I mean, I think we heard some of the things already, and I want to stress one point which I think is very important, is to understand digital twin as a system, right? I mean, it's easier said than done. We heard the term quite a lot in the last 2 days, but for me it's really a combination of a model, of course, which is for me a necessary but not sufficient thing in a digital twin system. So we have to think about what type of data do we need, right? And not what is possible, but again, what is necessary there. So you just presented it in your presentation as well, right? So define that, and also what are the real use cases that we can find, that we can define, which are relevant for industry, right? So thinking in that loop, I think that's still a challenge. It's easier said than done sometimes, so I think that's one of the challenges. Second point is, again, also referring a bit to what we just heard before, is thinking in the interactions over the process chain, right? So we see a lot of models, very nice models, focusing on specific processes, but what happens, over the chain? What are the interactions between the product models and the different process steps over a production line, as you said? It's maybe another thing. And last but not least, the third one maybe, is the aspect of what's the right level of detail, right? There are super nice models on with numerical models, discrete element models of whatever coating process or calendering process, very nice, but there are on the other side those black box machine learning models. And what's now the right level of detail for applications, right? Maybe the truth is somewhere in between or a combination, we will see.
Okay, thank you. Simon?
I have kind of a similar perspective, and I think the first big challenge is that we all mean the same thing when we say digital twin. You talk to different people, and they seem to have different pictures of it. And a digital twin contains a model. A model is a part of a digital twin, but it's also a lot more. A digital twin should represent some actual physical instance in the real world, so you need some sort of identification mechanism that corresponds to that thing, whether it's an asset administration shell or a battery passport, which I'm really excited to hear about this afternoon, if anybody's here for that. So we need to be able to identify it. We need to be able to query and assess previous data, that you don't only know what your digital twin is doing right now or an hour ago, but what was it doing last year at this time. The more data from the past you can have and run analytics through, the better it will be. And then, of course, the model, which is the famous part that allows you to make predictions in the future. So I agree that we should see it not simply as a model, but more as a system of things. And that kind of brings you to the second challenge, which is especially for battery manufacturing. They tend to be very complex systems with information coming from different material suppliers, coming from different equipment suppliers, and all of these things have to work together. And maybe you can get it working, you know, for the first time pretty good, but then what happens if you change something out? If you change a model, does the whole thing break? You know, how can we make sure that this is robust and that you can include information from a lot of different sources without breaking your overall system? So that's kind of my perspectives on it.
Thank you.
Yes, well, I agree with all the comments by Simon and Sebastian. I would like to add maybe 2 or 3 challenges. I think maybe the most important one is demonstrating in practice that with digital twins we can improve the manufacturing process of batteries. Right? This is the first challenge. Because right now, so for sure, there are a lot of potential in the methodologies that are being developed, but still there is not a clear demonstration that these tools can improve the technology, you know, in practice, right? For sure, this requires, I would say, a lot of, I would say, sub-challenges to be overcome, such as, for instance, data standardization, right, when we are doing manufacturing process acquisition. And another aspects like standardizing maybe the way that we model the different process steps, right? And quantifying also uncertainty related to the models that are being used to simulate each of the process. I believe that it's possible to demonstrate that, right? But we need to maybe collaborate more as a community. This is the first challenge. A second challenge is the accessibility of these digital twins to the entire, we say, battery community and stakeholders in general. So not only people who knows how to make programs, right? And how to use software. So we would like these digital twins to be accessible to also to experimentalists, right? To PhD students who are maybe synthesizing a material, right? Only at experimental level. So then it's very important also to think on ways of maybe developing kind of smart interfaces. Well, Elizabeth mentioned a couple of possibilities like with virtual reality, mixed reality, and so on and so forth, that can maybe help making these tools more accessible, I would say, to the entire community. Yeah, this is the. And third one, sorry. The chemistry neutrality of the manufacturing models, right? Because for sure, so these models are 100% related to, let's say, the chemistry that we're going to use to validate the models, to collect the data, to train machine learning models, and so on and so forth. But I think the one big challenge there is to make these tools chemistry neutral, right? That they can, I mean, maybe with techniques, emerging techniques such as transfer learning, for instance, right? That could be used to, you know, maybe you have a very good model for optimized for some specific chemistry, and then maybe you can transfer this model to other kind of chemistries, right? Especially when we are talking about solid-state technologies and so on, right? Yeah.
I can continue maybe. Well, first of all, thank you very much for the invitation and for having me here in the panel session together with the brilliant colleagues. I think the challenge is indeed, I agree with all the previous visions, and I would also highlight the interoperability. Of course, we are talking about different models, different processes, different technologies, sensors to be implemented, and then everything together needs to communicate in the same language and needs to work together to, at the end, have a better and more optimized process. So interoperability is one of the biggest challenges that I see, together with the sensor implementation, as we saw in the presentation of Elizabeth. Yeah, there are many sensors to be implemented to, for example, help in the quality control process, but which ones, where, how, where to locate them, that's one of the questions also that we are now understanding more and more. And also gathering together, I think that's a third challenge. I think industry, from all different perspectives, even automotive industry, they have already implemented many interesting and needed digital tools like Industry 4.0 and so forth, and these can be communicated, we can gather together, and we can understand these lessons to apply them to battery manufacturing.
Yeah, I completely agree, especially with this last comment. So about not just understanding, not just detecting a problem, but implementing these digital twins, implementing digitalization, modeling, and simulation to understand why that happened and eventually to prevent it. This absolutely agree, and I think this will be a great challenge in industry and in the software development. But of course, another point will be to look at multiple scales with one single simulation, right? And this is a point that's been touched upon already before, but integrating a model that can simulate a digital twin can go over from the single process of the single machine and then can be implemented up to the building level. And having this in only one platform will be of crucial importance, and of course it's a critical aspect that we should try to solve.
Thanks a lot, all of you. Yeah, you know, for me, it looks a bit like science fiction, I must say. It looks so ambitious and so complex that I'm really wondering, I have a question I would like to ask you, and maybe more for you, Nicolo. What is already implemented and what is already actually used in the ongoing projects for the gigafactories? Can you already point some very practical, well, without, of course, sharing any confidential information, but what kind of solutions are already implemented and available on the market today?
Yeah, so in the world of the automation, I just showed an example, right? What's been implemented is recreating our machines onto the computer, and not just at the CAD level, but also we make them run. So the actual machine behaves by the physical laws that regulate the real machine. And so this machine can actually be a close approximation of what's happening in reality. And what we do is also test the software and the mechanical design, and we create what we call a virtual commissioning. This will decrease drastically the commissioning of our machines. It will bring the time to the market. It will shorten up the time to market of the product. But this is what's happening today. But as a perspective to the future, the way we see it is this digitalization, this machine learning algorithm can help the automation, the industry automation, will be to have machine learning algorithms that make the process always better and better by the usage of the machine itself. And this can be done just by applying the feeding back of the data from the physical machine onto the computer and then back to the physical machine. And this way we'll create a machine that improves itself along upon operation. This will be the dream, right?
Any other comment on this one? Really, what is already implemented and what is already helping the battery manufacturing industry, and what are also your thoughts of what will be the next step, what will be coming soon?
So when I can comment also, I mean, more in the process simulation side is what I'm doing, in particular in the artistic project that was mentioned by Eli. So what we have developed is, I would say, of course, the digital twin work can be used in many ways, right? But I will use that word, right? A digital twin of the process, right, of the manufacturing process, consisting in, it's actually a computational workflow where you simulate the different steps, the mixing, the coating, the drying, the calendering, the filling, and then the formation. These models, they predict the electromicrostructure and the cell performance in 3 dimensions, right? And they are linked with each other. And this is actually, maybe to comment on your comment, Sebastian, this already exists. It's something we have done. And then so we have also developed a machine learning twin of this physics-based model workflow, right? Which of course has the advantage of making predictions with much shorter simulation times, right? Because once these models are trained, then in a few seconds you can get your answer, right? You can predict how a batch of types of manufacturing parameters are going to impact electro properties and cell properties and so on. This is what we have achieved so far. And then there is all this dimension of interacting with these twins, right? With all this virtual reality, mixed reality, and so on. With the idea is the interaction with this let's say digital world for people who are no experts in programming, right? And so on. Then what's coming next is for sure the demonstration that this collection of models, and I will say this is a general comment also for other efforts going on in Europe, the demonstration that this works for different kind of chemistries. And once again, we come back to the point of chemistry neutrality, right? Demonstration. And also a demonstration that these models can help at optimizing processes, right? This is, I think, is also a challenge. We have addressed that partially, and we have published a paper recently on that. by using synthetic data, I mean, data coming from the predictions of physics-based models. But still, so we need to, I mean, all together as a community, think a bit more of how to hybridize in the right way data sets coming from physics-based predictions and data sets coming from actual experiments and actual information from the pipelines, right?
Yes, I think it's a good point, and also something to raise that we're not the first people who want to do a digital twin for manufacturing, right? It's been done before in other sectors, and there's a lot of very good industrial solutions to do it. But what is missing, in my opinion, is the link specifically to batteries. Because batteries are extremely sensitive, complex systems, and there's kind of two approaches you can take for it. On the one hand, we can go on each individual process step and try to predict out what you get at the end. But we're trying to do something coming from the opposite direction, where you get a battery off of your line at the end, and maybe it doesn't perform the way you expected it to. Why? What could the possible reasons be? And really, it could be thousands of things, right? All of the different parameters that can influence manufacturing, and it's too much to really evaluate. So we're trying to use physics-based models of cells to run parameter sweep optimizations to match what you get out in your model to what you get on the experimental line, and then combining that with ontology-based knowledge graphs to say, okay, this observable behavior is probably linked to porosity changes, and that's impacted in these manufacturing steps and mostly by these parameters. And with that, you can start looking through your data and trying to find anomalies or problems in the manufacturing process. So yeah, I think it's, you can approach it from different ways. There's a lot of good stuff in industry already, but what we really need to do is link it to battery-specific knowledge and battery-specific models, which is still, kind of in its infancy, I would say.
Yeah, maybe one thing to add. I totally agree, of course, to those points. I think actually the IT technology, so to speak, right? That's there, more or less, right? I mean, in contrast to 10 years ago, we know how IT architectures could look like. We have OPCOA or other kinds of more or less open interfaces that we can use. I think that's fine. We can learn from other industries. They are all good. We also have seen a lot of proof of concepts on a laboratory or pilot scale for different digital twins, but then again this question is how to bring it into practice. But I want to add actually one other thing where I see this could be a challenge. This is the multi-criterial aspect of those investigations, right? Because what I see so far are often digital twins that focus on a specific final property or some kind of intermediate product feature or stuff like that. However, of course, there are dozens of properties that are of interest, right? If you look at I mean, I don't need to tell you, in the final cell there, maybe we identified 50, 60 different properties that might be of interest. And I'm even leaving out things, how energy efficient that was produced, what is the throughput time of all these things. So now do we need a digital twin to deal with all these kind of, factors? Probably not. But is there the one digital twin? I don't know. Open question and challenge, I think, for the future.
Maybe if I comment also, obviously I do agree with the comments so far, and it's true that digital twin is a little bit of a fuzzy word. Sometimes we don't know what it means exactly, but we cannot forget that digital twin is a replica. So it's a replica of the manufacturing of batteries. That is something that at European level it's already happening. So at the end we need to divide and conquer. So make it in small steps and understand it in each different levels very well, so that to go for this digital twin with all the comments that has been already mentioned.
If we continue in this discussion, so let's imagine that all the challenges that you are facing, you find the solution. What would be the actual outcome? What would that mean if we achieve really this full digitalization of the battery manufacturing process, and also connecting with the usage and the end of life phase and so on? So what would that bring? What would that offer you as added value?
I mean, one obvious thing, but that's pretty clear, is of course the exchange, and try to not reinvent the wheel every time again, right? Obviously, there are a lot of approaches we can learn from each other, can adapt it to the specific cases, and potentially, and there are projects like for that on a national and a European scale to connect different models, right? So Alejandro was doing some things in France there as well, other people as well. So that's interesting, and that's definitely an added value of being in such an ecosystem here. And by the way, that explicitly includes also industry, of course, right? So to really ensure that those more academic-driven models, which I obviously like as well, but how to bring it into the practice and to bring in the requirements of the industrial application.
It's a very nice question. I was actually doing an analysis the other day on what impacts stuff like this could potentially have. And because of the size of the battery market, and especially how it's growing, if we can improve the yield of battery gigafactories by just 1%, that translates to hundreds of millions of euros saved across Europe. And I mean, it's a huge potential benefit for the payoff. And of course, the catch is that it's not easy to improve the yield by 1%, but every tool that we have available to do that is helpful in getting there.
Yes, I agree for sure. So what I would expect from these digital twins is, for sure, as I was mentioning at the beginning, so showing that we can improve, manufacturing process, and I would say also quantify the degree of this improvement, right? I think this is a very, very big challenge that we have. But also, what I expect is maybe a better reusability of the tools that are already available, right, in the community, as Simon and Sebastian mentioned already. This is very important to avoid reinventing the wheel, for sure, but also to prepare the next generation of technicians, scientists, and so on, who are going to enter in this field. So, as you know, so there are many gigafactories being planned. Some of them are already being built. And we have now facing a lot of pressure, right, to fulfill this requirement of the next generation of technicians and so on. There is a kind also of, I would say, talent war. I mean, different companies trying to, hire people, for specific skills. Therefore, I mean, as academia, so we need to produce more talents, right? I mean, to try to fulfill the requirements. So I think it's also another challenge that I hope we will be able to accomplish, to overcome.
I totally agree with that last point from Alejandro. And yeah, definitely if we would have a digital twin also, apart from the optimization of the battery production, of the optimization of the battery product itself, I really think it will be the enabler for recycling. The more we know about manufacturing, the more we will have a clear vision on how to recycle and everything on that still needs to be discovered.
Yeah, exactly. So same point here. Zooming out a little bit, not just looking at manufacturing, but just also looking at the whole cycle life assessment of a product. If we imagine that in future battery will not only be a physical device, right? It will be a set of data that while the battery is being produced, not even the battery is being produced, while the materials are being mined, will start storing data into somewhere through an appropriate infrastructure, then we know what happened to that device, and this will, I think, really help the second life usage and then recycling. Then we'll have a much better and more intricate collaborations between the different stakeholders, and in the end, the final result will be cheaper batteries because we can recycle, we can reuse recycled materials. It will be second life, and in the end, this all concepts are at the base of the battery passport. I mean, there will be a session later on, and what's needed for the battery passport to be a real thing, it will actually be digitalization, right? It will be data stored across the whole cycle life of the battery, and this will be hopefully a bright future.
So I forgot whether it was Elizabeth or yourself, Niccolo, who pointed out the importance of this, or maybe both of you did it, the data management. So about how to maximize data acquisition, data reliability and qualification about the reliability of the data, and also how to reuse this data into for training the machine, and now you are coming with a dimension which is not only during the manufacturing step, but also for the full life of the battery, keeping in mind all this data from the origin, from the manufacturing, up to the use and until really the end of life, and how this could be fitting and used in the battery passport that is also under construction. So my question now is more, what about this, regarding this data management, where are we? You mentioned this ontology that we need first to speak the same language, Simon. What are really the remaining big challenges to be addressed regarding, because at the end of the day, I understand that all of this is driven by data. So I think yesterday in a session, somebody highlighted the classical way, if you put garbage in, you will get the garbage out, of course. So what for you would be now the main important topics really to address to improve all this data management?
Yeah, so yeah, with ontologies is a great tool to be able to improve the interoperability of data. And there's two ways you can go about it, right? If we want to say, you know, we want to make sure that all of our data works well together. On the one hand, you can try to enforce standard data models. And maybe, you know, you can get some of the community to adhere to it, but it's never really going to work, right? There's always going to be somebody who wants to do it their own way. And really, it's kind of a good thing, because if everybody's doing the same thing, you lose the innovation, and, you know, you lose that opportunity. So we don't want to do that. We don't want to enforce standard data models. What we want is to be able to give you the tools that you need to describe your data using the same terms, and be able to make sure that other institutes or other processes will understand it. So you can think about it like a language, you know, that has the same vocabulary, it has the same grammar rules, and if your data speaks the same language, then you can use it in different sources. And there's a lot of really good work being done on that already, especially for battery manufacturing. I can point you to a nice website that's developed by Fraunhofer ISC called KI Probat Wiki. And that was developed by Simon Stier and his team. And they have a really nice interface to explore all of the different aspects of battery manufacturing and the different parameters and what influence they have on the overall cell performance. And this is kind of one thing that we're making a lot of thoughts about right now. On the one hand, we can use ontologies in a machine-readable way for machines to access it, but also, you know, this can be a big advantage for humans. And how can we create a good human-readable interface that it supports learning there as well? Yeah, so that's kind of my perspective on things, but.
Yeah, if I may, before asking the opinion of others, I would like to come back on some of your points. You said, okay, you don't want to impose these ontologies, but more to invite really and to have them people joining more on a voluntary basis. But you were talking also about vocabulary and grammar, and in every country there is some kind of authority who is addressing the correct way of really writing and speaking. So do you feel that we need that kind of authority, or is it something that will come spontaneously from the different stakeholders, so that at the end we are converging? I'm guessing that there is not only initiatives here in Europe, but there are also similar initiatives in the States or in Asia, and that we at the end we might be with different languages that will bring additional challenges. So.
Yeah, for sure. I mean, there have to be rules, right? And we want to keep the set of rules as small as possible in order to facilitate, you know, innovation and expansion. But at the end of the day, there have to be some rules to make sure everything works together. And within Europe, that role is filled by the EMMC, the European Materials Modeling Council, who support the development of the EMMO, which is our top-level ontology that everything else kind of branches out from within Europe. So yeah, as long as the different ontology development adheres to kind of this basic set of rules so that everything fits within the framework of the EMMO, then that's fine. But, you know, as with other things, there's not necessarily, there's other top-level ontologies that are possible to choose from, and being able to map terms across different ontologies is a good way of dealing with that. Well, that's kind of getting into the technical details. And yeah, fundamentally, ontologies need to be community-driven things. And we try to include as many different kinds of voices as we can in the initial development. And now, as we're moving from initial development towards use and demonstrators in the community, we want to invite as much feedback as we can get, either through our GitHub repo or through our wiki pages that we're making. And yeah, ultimately, it needs to be able to meet the needs of the people who will use it, and we're trying to facilitate that as best we can.
Anybody would like to react or to comment on this? Yeah, Alessandro?
Yes, I fully agree with Simon. So I will add also the importance of sharing the data, right? For sure. I will comment one example. I will give you one example. So regarding, for instance, the lifetime prediction of batteries, there are very few repositories available online to do so, right? And then many publications, from academic side, so they will report machine learning models and so on, always trained with the same kind of data sets, right? Where we don't have any information about, for instance, the electrode formulation, right? We have also we have published a paper last year it was a text mining study. We screened something like 20,000 publications on the lithium-ion battery and sodium battery field. And we found that 96% of papers, they don't report the electroporosity, right? There are maybe more than 90% of papers that don't report the electrolyte volume, right? That was used to prepare the coin cell, for instance, right? So I think also this calls for standards. Several journals now that are pushing in this direction, right, to standardize the way we report the data. But I would say it's even more important to share the actual data, right? Not just to reporting the data nicely in a paper, but share the raw data, even the mistakes that you do as an experimentalist. Because this is even more important to train any kind of machine learning model is the failures, right? They're more important than the successes, right? I think Michael Jordan used to say that when he was saying, someone was asking him, what is your secret to become a champion and so on? It's because I failed many, many, many times, right?
Yeah, totally agree with the sharing point, and also on the sharing of the failure that will make all go farther, faster.
Maybe also in addition to that, that's the perspective on sharing data on models and improve models, but also there is this elephant in the room, let's say, sharing data in production over the whole value chain, right, which is connected. And of course, we all know these issues. Do we want to share? And I'm not talking more about the industrial perspective, right? Do we want to share this data? And what type of data? Do we just talk about the origin of the material or the environmental impact, the backpack, let's say, that is there, that's going to the OEM, and they can do their calculations for the carbon footprint? That's maybe, okay, that's one thing. But even more interesting from a technical point of view would be maybe quality-related data, right? So that this batch of material or this even specific cell, now dreaming a bit, but we have a specific...
You're touching some touchy information, which is also related with a competitive aspect and
exactly.
And so, yeah.
And this could be then brought in conceptual, at least that totally makes sense, of course, to bring that in a specific model in the production that okay, this batch has this properties, so I use this value to calculate further on in my digital model, and so on and so forth, right, through the process chain. But okay, I think we are not there yet in real life, let's say.
Yeah. A comment from the industry on this one?
Yeah, absolutely agree. Not only about academia sharing data to improve the knowledge, absolutely, but also I like to touch upon the recycling of the products, right? So you have different OEMs that they make different batteries, different battery packs, and then how do we recycle them? We just tear them apart and that's it, burn them down, but if we only had the information on how that pack was made, it will make it easier to open it up, to take the cells, and then to recycle everything. And again, not only when it comes to information, like protected information, but just really a better way to understand how to dispose and how to better reuse the batteries after they're made. So yeah, it's not only about speaking the same language, but the willingness to speak, right?
And how could really industry and academy better work together on this kind of approach? Do you have some insight on that?
Yes, I think definitely this is a must or a need. I see that we can collaborate in different ways. Obviously, for battery production, we need to have like small scales at academia or research centers where we can prototype or where we can adapt all these concepts that we are talking, and then have, let's say, a more mature version that can be installed in a real production line. On the other hand, as well, I see that we need to focus on it on the different steps individually, like slurry mixing, calendaring, drying, so on. There we have individual equipment that works for developing those specific steps, and there I think a win-win between academia or research centers and the industry can very well work together to improve that machine or to improve that specific step by reducing the energy need, by being more efficient, by being more accurate. And then finally as well on something that Alejandro already mentioned, on education. We need to have an understanding that also was mentioned today in the morning in the panel. We need to understand what the market needs. And then at the end, we need to have students or people that will work on those companies. So we need to have a very, very close collaboration to provide to the industry what is needed with already prepared and professionals people from the academic point of view. So I think this close collaboration is really needed right now.
Yes, please.
And I think there is also, besides this research and technical aspects, which are obviously very important, there is one very obvious thing, that's education, right? As someone said before, right? So in the universities, we teach, hopefully, the future engineers also for battery manufacturing. And I think there could be a stronger alignment, to be a little bit self-critical there as well, obviously, between the needs later on in the battery manufacturing industry specifically, right? A lot of education is coming more from the product perspective, and electrochemistry, all good, right? We need that, don't get me wrong. But now here we are talking about battery manufacturing and the specific aspects there, and I think that could be even better aligned also in the curriculum of universities, right? To more tailor that to the needs in the European industry in future.
Yeah, I think that's indeed a very important point, and this education and skills aspect are absolutely critical. If we don't have the people to implement and to develop these approaches, of course, nothing will happen. I propose now maybe to move to the questions from the audience. So, okay, one first question there, another one there, another one there.
Okay, Andreas Hutter. I'm working at CSCM, an applied research lab in Switzerland. So I very much like this idea of having this digital twin of the battery when it comes out of the production, because I would like to use this in my BMS system and to have a physical representation right from the start. So now when you talk about a digital twin, the twin lives out of what you give him to eat. Now, in the lab, we know all to do the fancy lab tests. It's mechanical, it's electrical, it's optical. And in the production, you would like to use the quality sensor or the quality inspection control sensors that are already there. So now my question, where are we today to know which kind of sensors would we like to have in the quality inspection line? And where are we also with integrating them? And what is the opportunities that come out of that for industry to make new machines, to make new sensors, and to integrate them in the machines?
I think it's an excellent question. So maybe I can point you to a paper that we have published with the Lithium Planet network. You know, it's a European network about power lines. And And this paper, what we have done is trying to classify the different data types, that you can acquire all along the process in terms of the criticality, right, to develop different type of digital twins, but also in terms of the accuracy and the speed of the acquisition, right? And in the paper, you will see some kind of tables with some, color codes, and in red, so we try to indicate the ones where efforts are needed, right, in terms of sensors, right? Because we would love to have acquisition method that can on the fly extract the electron microstructure in 3D, right? The electron microstructure coming out from the oven, for instance, right, or from the calendar machine. It would be fantastic being able to perform online tomography, right? Because this is the ultimate way of validating physics-based models, which are 3D resolved, right? Because if these physics-based models which are 3D resolved are properly validated with the real data, the data we need, then we can use them to produce synthetic data and to complete the experimental data sets and then do a very sophisticated machine learning for optimization, right? This is one example I'm giving to you. A lot of opportunities there on microstructure characterization on the fly, if possible, right? Very challenging, methodologically speaking, for sure. And also, well, there are many other parameters are very easy, right? Easy, I would say. The thickness, of the coating, right? Is already something that we are able to do, right? But to validate the physics-based models, we need more than that. We really need information about the microstructure. By knowing that characterizing, a microstructure with state-of-the-art tomography technologies is very challenging because you have the problem of cementation of the different materials that you have inside and so on, right? So I think this calls for methodological developments, right, for sure. Yeah, I don't know if someone wants to add something.
Yeah, great point. Yeah, sure. I think sensors are a big part of the machine manufacturing. The machine that manufactures the batteries. And the hardware, yes, it's there. It's not big. It is a challenge, but with the production cycles that we have, there are some sensors that can be used to keep up. But the real point is, we store the data, it's there, we understand whether or not to reject the product, but can we elaborate the data and learn from the data to avoid the mistake? And this is regarding the production of batteries. But how about the real device, imagining to having the batteries with the BMS, right? And having a BMS that understands how the battery is working and maybe communicates the data to a server. And then we can even create some sort of network of different batteries all stored to one server. And then we can do modeling on that data. And we can maybe link this data to the production and really create a network of performance, not only at the final product, but at the early stages for the manufacturing. So exciting perspective, and for sure, censoring, it's very important.
Okay. Another one? Here in front. Oh. Yeah, please.
Thanks a lot for all the explanations we had today. I agree with what you said up to now. And I would like, so I'm Elise from NG Laborelec, so an end user, industrial, and for stationary storage mainly. So of course we have the digital twin here for the manufacturing aspects, and then it's key also to understand and to prepare the recycling later. It was also mentioned that it's also key to predict the performances and so on, and you properly say that, 40 situations are not reported or are not in the data. So the point is, if we can predict a normal situation, is it also possible to predict an abnormal situation during a usage? And if yes, is it already done, or is it still a challenge to collect the right data at the right place? Thanks.
You're referring to the use of the battery, right? So in the use phase, of course, our focus was more on the manufacturing side so far. Maybe from that perspective, yes, there it's possible, definitely, in the sense of course, running scenarios. You can incorporate uncertainties in your models, of course. So, and I personally also believe it's not always in those models to just calculate the one exact value, which is not realistic, right? It's about trajectories, so robust directions that you can deal with, and then come to a decision. That's the answer for the manufacturing part. For the use thing, I think on the higher level, it's the same answer, right? Of course, there are approaches where you can simulate the behavior in the use phase as well. And then it's about considering the uncertainties through proper simulation approaches and stuff like that. But any other comments to that, just from the use phase?
I mean, to predict failures, for sure, I fully agree with Sebastian, what he said. But once again, we come back to the point of the importance of sharing data, and in particular data related to failures, right? That in publications we don't see so much, right? Because we see the best results we can obtain, you know. But yeah, it's very, very important. Then these kind of models, if we do so, if we share the failure data. That's something.
Maybe one addition, actually more referring to the last question or the combination of both. What could be interesting is also in the end of the production line, maybe we don't need to have all the data from all the different production steps and push that forward along the value chain. Maybe it's good to have a surrogate model, like a representative model which depicts the behavior of that cell depending on what happened to that cell before, and that's maybe sufficient for the later stages. Question mark, but yeah.
Okay, yeah.
Okay, thanks for the discussion. I'm Arpit Mishra from ABE Group. So you guys talked about integrating these multi-scale physics-based models to this digital twin. So I would like to know how challenging it is to integrate these different length scale of models ranging from electronic level to say cell level, and overall how to tune the overall accuracy of the model. For example, a different length scale model will be more accurate than the other scale. Can you please enlighten on it?
Oh, okay. Well, thank you for the question. Yes. Well, it's something that we are working in the artistic project on this kind of thing, right? For sure. I mean, how to connect the models in a smart way, how to validate them, right? In the artistic project, we decide to work mostly at the mesoscale, right? Because we intend to predict, 3D morphologies. I mean, the 3D microstructure of the electrodes, right? And so on. I would say one remaining challenge is somehow developing kind of multi-fidelity modeling approaches, right? So in a way that when you are simulating a given process step, right? Maybe sometimes you don't need to go too much into the details, right? You are not interested in predicting the electron microstructure. Maybe you are interested more in predicting the thickness, and that's it, right? Then, so in that situation, so you will use maybe a simpler model, CFD-like, or so on, right? I think a methodological challenge is maybe designing a kind of a smart workflow that can actually deal with different type of models, simulating each process step, right? And then deciding maybe putting on top maybe some kind of automatic process to decide, depending on the kind of experimental, the quality of the data you have at the experimental side. This system will help you, to pick the right model, right? To simulate and to make predictions in the right way. So there is some work in progress in the artistic project. This is what I can comment, right? In this sense. And also regarding the derivation of surrogate models, Sebastian mentioned that also very well. I mean, models which are basically machine learning models which learn from the data generated by the physics-based models, right? This is in artistic we are doing as well, because the advantage of that is that you can actually run the simulation in a few seconds, and then you can integrate this model into an optimization loop to fit the parameters of the model, right? Because you need to compare using experimental data. And then you can eventually use the same model for doing optimization of a process, right? Because to do optimization, you prefer having a model that has very little computational cost, right? Yeah.
Thank you. Simon?
Yep, and I'll just supplement that and say one of the other factors that we consider is value of information, right? You can collect all of the information, all the sensors imaginable, but does the cost of collecting that information or does the cost of running that model outweigh the value of what it ends up providing you in your digital twin? So on the one hand, of course, it's a question of how can we make the digital twin the most accurate and the best predictions possible. But on the other hand, how can we balance the cost of collecting information with the value of the information that it provides?
Yes, please.
Yes, hello, I have a question. My name is Vincent Herries. I'm from CA. I'm working on BMS algorithms, and I have a question about data collaboration and exchanging data, because you are talking a lot about artificial intelligence. But to program this model and to feed this model, we need a lot of data. And currently, it's not available, this kind of amount of data. And who has this data? Also the automotive company, and they are not really willing to share a very large bunch of data to fit this algorithm. So how do you see we can move forward on this aspect to really produce accurate and generalizable model of based on AI?
Coming back to data sharing, yeah.
Yes. So data sharing is the key. So I think we need to maybe, this should involve policymakers and so on, right? And maybe forcing researchers. And, we want to publish a paper, sharing the data, sharing the raw data, the failure, and so on and so forth. It's emerging. These kind of initiatives are already emerging in some journals, and it's very good. But we need to reinforce even more that. I think this is the only way. And I have maybe a comment on why you say that we need a lot of data or big data. This is generally is not true, right? So you can have surprises sometimes. I mean, with very small data sets, if your data is high quality, I would say it's very important the quality of the data, even more than the quantity, okay? Quality even more than quantity. You can sometimes derive some nice machine learning models that for sure they will not be super, generalizable, and they will not deal with a lot of parameters, but still they can be useful for providing some kind of guidelines when you are trying to optimize a process step. Yeah.
And I'd also agree with that. That on the one hand, we're trying to reduce the number of parameters that you need for physics-based models, and if you can get close enough, you can apply some fancy numerical methods to match the performance that you see. So trying to reduce the parameterization burden, especially the teardown, destructive parameterization burden. But at the same time, there is kind of a growth, and I mean it's slow and there's some resistance to it, but there is a growth in sharing physics-based parameters. In the UK, they have a nice initiative called LionDB that shares physics-based parameters for battery models. There's increasing amounts of testing data, like proper electrochemical testing data available for commercial cells that's starting to be published. So I think if we can kind of combine those and say, okay, we're going to make a little bit more data available and try to reduce the parameterization burden that we have, we can find a happy medium.
Yeah, maybe just a quick comment from my side. So we have a need for data that apparently nobody wants to give, right? So what can we do to, make people share this data? We can either, just do a law, and so you need to share your battery data. But how about creating an infrastructure that in an easy way, in an easy fashion, everybody can just insert the data of their batteries. Maybe this data, it's not revealed to anybody, it's encrypted, and it just goes to the model that releases the output without violating any IP. And maybe in this way, we can actually realize the data sharing. We can actually make this possible. So I wonder, what are the initiatives that can make data sharing more available? What are the initiatives from the European Union that can make this happen?
I think this will be maybe Sebastian.
Yeah, maybe in that line. I also think we have to face reality. There will be cases, many cases where there's no interest to share the data. However, I think what we can provide as a community are clear recipes and procedures where, similar to what you said, where it's then easier for a company to say, okay, I just apply that to my specific field. Yes, I use my data, but the principle behind it, the ideas behind it are very similar, so at least that facilitates the implementation of that kind of procedures internally. Of course, from the big picture would be great to share that and have more generalizable models, but there are some limits to that, I would say.
Yeah, but I'm sure that battery field is not the only one where we are really struggling to get this and to find the appropriate model and infrastructure that really would really allow to really to merging the best of these two worlds, really those who want really to keep the data confidential and those really who need this data to build and to accelerate the development for the benefit of the society. So, well, I think that's not, that's for sure a need on our side. I'm sure that there are other fields who are also struggling for that, and hopefully we will see some common initiative at the EU level that will also be addressing and facilitating this in the most, we live in a win-win situation. I think that's really what we should be really striving for. I'm afraid that we will have to stop now. I'm sure there was still a lot of questions, and sorry for that. Maybe one last one? Yes, one last one.
Yeah, I'm so lucky I can ask a question for the last one. I know that there are some research in developing digital twins for applications, for example, for the batteries in electric vehicles, and they also work in developing digital twin for the production line, right? So what are your viewpoints? How can we close this loop, right? For example, if we see some problems or some disadvantages in the application, how can we determine which parameters in the production line we should tune to get a better battery? Thanks.
Yeah, just in first comment on that, I mean, it comes back to the issue of traceability, of course, and so can I trace back really this specific module or cell in the application, trace it back to the specific production process even, and point of time, and so on. For me, it's still a little bit the discussion at the moment, what level of detail do we need and want there, right? Because it can be in all the details, but maybe that's not necessary, right? So so that's one part of the challenge we have to solve there. And yes, then I think it comes to the point of those kind of initiatives that we see in other industries and other areas, like this international data space community, how to share the data on platforms, to make it accessible later on and things like that. Or in Germany, it's Gaia X and those kind of things where it's about sharing the data and using the data in later life cycle stages and stuff like that. So I think there is some work to do to link that to the battery field as well, whereas I'm aware of some first things happening there. Yeah.
Okay, this time I think I have to close the session. So thanks a lot to all our panelists for your very inspiring contribution. Thanks a lot for the audience for your very challenging questions. And I really invite you to also to join the session this afternoon on battery passport. That will be a little bit taking the same topics from the other viewpoint, coming really from the device and not from the manufacturing part. So. Have nice discussions now, networking discussions, and let's go for lunch and meeting again at 2:40 this afternoon. Thanks a lot.